So my name is Yehuda Elmaliah. I will present here today SLAM solution. So now talk a bit what is SLAM, okay, and a bit of the solution over the years. So before we start talking about SLAM, first we'll talk about robot autonomy. In any mission of robots that need to do it and to work in autonomy in autonomous way, we will find the same building blocks repeated. When I say robot, I mean mobile robot or something like that, not the industrial one. Okay, so we will find the same building block. The robot needs to know its location. The robot needs to know how to recognize obstacles. The robot needs to navigate, to calculate a path. It needs to take decisions along mission. And over all of that, now program your mission. But what I say are the significant building blocks that we need to solve. And the two building blocks today that we are talking is mapping and localization. There are a lot of packages over the internet, over ROS. You find a lot of packages of SLAM, and you can put and you can do a demonstration. But still, this problem is focused on research, and there are a lot of new papers on SLAM, okay, on the problems that I will present today, which means that this is not a solved problem yet in any case, because I will talk about it at the end, about a bit of the conclusion of this problem. So first we talk what is SLAM. I'm sure that there is an expert in SLAM.
Possible. You can stand here, we'll see it better in the video afterwards.
Ah, okay. So I'm sure there are a lot of experts here in SLAM, but I will talk to somebody that doesn't know what is SLAM at all, and try also to enter to the formula in this presentation. So SLAM is to be able to estimate the position of a robot and the map of the environment at the same time. So the robots need to know its location, and also build a map. So the problem considered as a difficult problem, because in order to be able to localize yourself, you need to know the map, where the map is, and then I will localize myself on the map. In vice versa, we need to, in order to build a map, we need to know where we are located on it. So it's even call it the chicken or the egg problem. Oh, give me the map, I give you my location. Give me my location, I will give you the map. In SLAM, it's you don't have the location, you don't have the map, and you need to do it simultaneously. That's what we call SLAM, simultaneous localization and mapping. And a bit about the concept of SLAM is robots start without knowing anywhere. Now he open his sensors and see everything. When he start its location, let's say we are in indoor, there is no GPS signal, we don't know anything. So when I open my sensor, I can see objects, I can put them in the map, in a new map that I build now. Okay, this is what I see. Then the robot move a bit. Okay, now he need to localize itself in the previous map that he built, and also he see another things that he didn't see before because he moved to another place, and he need to find where he is located in the same way it is located in the same map. So let's take those three examples, a belief of the location of the robot. So you will see here, you'll see this is the gray, this is a gray location, this is the first location, the second and the third. He doesn't know really where it is, but those are three beliefs. This is the location and the orientation of the robot where it looks. So when it moves, let's say delta x, delta y, delta theta, this is what he thinks by its movement. Then it moves itself over the second stage here. Here it moves to here, and this is the movement here. Okay? Then he open his sensors and start to recognize landmarks, obstacles, something that you see in the previous step. And in the previous step, and in this simple example, we will assume we have two sensors, let's say two sonars, and now it feels obstacles. It open with these sensors. You look at the map, and it sees that it's correlated here to its location. You see here, so we accurate. This is a good expectation where I am located. Okay, and here, oh. And here it doesn't fit good to the location, but it's quite close. There is a epsilon space between them, so we understand I'm quite close. And here, this is not really my location. So this is the concept of SLAM, and you do it iteratively from step to another. This is the main concept. Now let's look about this example. It's FastSlam, an algorithm that do that. They develop it here for the rover in Mars to localize itself. And what you see here is it always recognizes these landmarks and localize itself based on the landmarks that you already see. And the gray one, the blue line is the location by odometry only, which you see there is no correlation to the location. And the green one is by using this landmark and what you, as I explained earlier in the concept. And the red one is the relocation. You see it's very accurate, while you always correct yourself based on what you see. So if we look at the SLAM, there are a few families. There is the filter-based solutions, which you can find Kalman filter, particle filter. I will talk about them. And there are a lot of algorithm, G mapping, that you can find also in ROS, is a particle filter base. Kalman filter, you can see Hector that Hadar talked about it earlier. It's based on Kalman filter. FastSlam, the movie I showed earlier, is based on Kalman filter and particle filter. So that was, there are a lot of algorithms in this family. There are also a global optimization algorithm. I'll talk about them later. And now a newer one, it's called the CNN SLAM, based on neural networks SLAM. So let's talk about a bit about terminology in SLAM. Let's denote xt to be the location of the robot at time t. Okay? The location, it's in x, y, and theta. This is the location of the robot. x1 is the location of the robot at time 1. ut is the motion model. It's the motion of the robot. ut, the motion of the robot at time t. So it starts in a specific place. Then in u1, it moves a delta x, delta y, delta theta. You can get it from, somebody can help me? Odometry. Okay, from IMU, movement by IMU. Okay, this is you can get it by the IMU or odometry or something like that. ZT is is what the sensor, the measurement sensor say. Measurement sensor, for example, LIDAR, depth camera, yeah, sonars, I don't know. Okay, so this is Z. Z is the measurement unit. ZT, it's what was the measurement at time t. And then we have a maps. We have map M1, M2, etc. Those are the maps that the robot start mapping while it moves. Okay, and L, we can also look at landmark map and not just obstacle map. It depends the mapping and what we need from the mapping. A bit about maps. What you see here called occupancy grid. Occupancy grid is a grid, a 2D grid, that in each cell we can color in 3 colors to choose one of them. White, there is no obstacle there. Black, there is obstacle there. Gray, we don't know what going there because we didn't measure this place at all. So the occupancy grid is also a probabilistic because in each cell we have a number. Let's say if I see a cell 9 times that it was free and 1 time it was occupied. So the probability of this cell will be 0.9 to be occupied. Yeah, occupied. Yeah, that's what I understand the concept. Okay, and this is and then we present the map based on the occupation, because if I see this place and it is always free, then a person moves. Okay, and now I see it's occupied. I will put it to be occupied. No, we want a robust map, not a map that changes because of small changes. That's why we collect the data as a data probability data. Another way to save maps is in point cloud. You can catch it in a point cloud. You have a vector of, you have an array of points with x, y, z location. This is one. It's difficult to find in this in the point cloud data structure. A very useful data structure for maps in a 3D. We call it a 2.5D. it's the elevation map. The elevation map is a map, it's actually a grid, that in each cell at the grid there is a height. If written there 1.5, it means from 1.5 meter to the earth, there is something, there is an obstacle. Okay, so it's very easy to calculate and to do in real time calculation and navigation on those kind of map. But the problem is that it's not fully 3D. It's not fully 3D because if we try to put a bridge there and there is a quadcopter that they need to navigate there, I can't understand if I can go behind because all the bridge will be occupied. Okay? There are another data structure called multi-level surface map, which allow us with few levels of elevation maps, and it gives you a bit, it's 3D, but it's not so accurate 3D as the octo tree, that I will explain now. Octo tree is also a map that we catch it, we look as a cube. You see here in the example as a cube. We divide the cube to 8 small cubes. And the big cube is a node. We represent it as a tree. Each tree has 8 leaves, and each leaf also is a cube, and it also has 8 leaves, etc., until we arrive to a specific cube that represents this. So we don't open all the space, but if you take this cube and you see this is all this 1 divided by 8 is 3. Okay, there is nothing there. I don't need to divide it again. So what I see, the relevant sun is white, is a leaf. Okay, so it's very sparse data structure, and it's quite good to represent it a 3D map. And also we can define the resolution if we want until a specific depth. So we can also define the resolution of the 3D that we want to catch. And here you can see an example, not for SLAM, but in a real time using an elevation map. You see this robot moves 2 rotating leaders here and here, and it moves, and see that the elevation map here, what he sees, he understands, I can go, I can't, and build this map. And 2.5D actually in practice very useful as a map. Okay? And a bit you will see that this is not a mapping, because only it projects what it can gather from the leaders. Okay, so this is what it sees in front and back, and this is using the elevation map. So terminology about SLAM. Okay, PZT given XT, it means that what is the probability, or we can look at, let's look about this is exactly the same. So what is the probability that we are in location T, and M is the specific map, and ZT is what we see. Meaning that I am the robot, this is my sensor, okay? And I'm standing here, this is the map. And what is the probability that my sensor touch now an obstacle? In this situation, it's 0, yeah? In this situation, what is the probability? 1, because my sensor, catch and touch an obstacle, okay? So what is the probability now if my sensor touch an obstacle? It's not 0, it's not 1, but it's quite close, because if I move a bit, it will be very close. So if I do a small search around the map, I find that my sensor can catch this obstacle. So this is PZT given XT. What is the probability, okay, of when we are in location XT, and this is the map, to read ZT. This is the observation model. The motion model is what is the probability to be in location XT, while in the previous step, my location was in XT minus 1, and I move delta X, delta Y, delta theta. What is that question? What my probability? Because if I was in XT minus 1, and I move delta X, delta Y, delta theta, I can calculate it where I am in XT. But now, if it's accurate, yeah, and it's very, yeah, of course, it's depend what is the environment, okay? It's depend the robot itself. Maybe we have a robot that go very accurate when it moves straight, but when it take sharp turns, it loses its the accuracy. So it's important also to make it and make it very close to the specific target robot. So those are the basic of the observation model and the motion model. And now we'll talk about the belief. Now each robot, the robots calculate it, need to calculate its location. It has its belief how accurate I am, how I think that I'm in the location that I think I am. So the belief xt, the belief that I'm in location xt, meaning what is the probability to be in xt, while given all the reading from starting, all the readings, all the sensors reading, and all the movement motion. This is the belief. And in order to calculate the belief, we will use also a predicted belief. A predicted belief xt means that what is the probability to be in xt, while I get all the information of sensors reading from 1 to t minus 1, and all the movement until t, without the last reading. Okay, this is the predicted belief. And when we enter it to a formula, when we want to calculate the location of the robot, we will take what is my belief now in xt. We will look it's depend on the belief where I was in xt minus 1. I'll take the belief of being in xt minus 1, and I multiply it by the probability of the movement of the last step. This is the motion model. So what is my belief here? Then I move to xt minus 1. What is my probability? What is the probability to the accuracy of the movement? And all of that, we will multiply it by the probability of the observation model, how it fit to the map. And since it always a multiplication of frequency, so we need to put here a normalization factor. The normalization factor gives it the right number. So this is the iterative step. In each step, we do that. So enough for the mathematics. Okay? That's all. And now what I told you here, we will see it in a movie. Okay? Hamster is a platform that we are selling in Cogniteam. We develop it, and it's actually for programmer, developers, students, academia, companies that want to do and program robots and don't want to solve the basic problem. They want to show the specific mission. Let's say I have a robot that need to patrol in places. This is the algorithm I want to invent. I need to know my location, to take decision, to calculate a path, etc. And the Hamster already everything implemented in Hamster. Just write in the API what you want to do, and it's solved. So what I'll present here is only localization. There is a given map. Okay. Stop. What you see here, those are the particles. The particle is the location of the robot. The robot doesn't know where it is located. Okay? But you think, maybe I hear. A lot of dots, green dots, are the particles. What do you think it is? Now we start moving. Move to a specific location, exactly what we see. Each particle, we think that you have an array of particles that have x, y, theta, and belief. Now I am doing a next step. So I need to update each of the particles, write a loop that updates all of those particles. So what I give to each particle, I tell him, you move delta x, delta y, delta theta, and this is your new reading. You take the belief, multiply it, okay, move the particle, and give a mark of how it fits to the reading. What you see here, this is the map. Okay, the red, we took here the best particle that we have by its belief, or there is also a problem how to choose the best particle, not the best particle, the best belief, maybe. But if the best particle was here and his belief was 0.9, and there was 10 here with 0.89, okay, which we prefer to be its location. Probably the group Okay, so this is another problem to choose the best particle. But let's say here we took the best particle, and this is the reading of the leader. You see, it's not accurate. It doesn't fit exactly. See here, there is no obstacle here. Okay, and what you see, this is the best fit that he finds. Okay, so iteratively, in this way, we update the particle, the robot moves, and always the particle updated, and there is no accurate fit to everything, but it's the better one than the others because. Okay, and this is a mapping. There is no map in head, and now the robot maps, and I will show you something interesting here. Now the robot moves, it maps the environment, and in the mapping, as exactly as explained in the localization, I am moving the particle, update its belief, and also add information to the map. If I didn't see in previous, I am update the map to a specific thing that I see now. And now you will see the robot moves. He will build this room, and will be something interesting when it will enter to this room. Not here. Okay, now it enters to this room, and oh, you see what happened? The map the map is broken now. It's not very good. It chooses a particle, a not very good particle, and there is a problem. And then you will see, you will jump now. You see what happened? Oh, no. And now we will jump and fix it. You see, fix it. Why? How we fix the map? Because it's fine that the previous particle was not the best one, and it replaced particles. And now this is the better particle. So in mapping and not in localization, each particle have its own x location, y location, theta, and map. There is no single map in particle filter. In particle filter, each particle has its own map. So if we have 100 particles, we have 100 maps in memory. Okay? This is how it works, let's say G mapping or something like that. Hector SLAM, what it do, it have its own location. It's not particle based. It has its own location, single one, and it get the information for the IMU. Okay, get the information from the IMU, enter it to Kalman filter, get the leader scan, and find the best accurate. Also enter it to a Kalman filter. It get its accurate location. You do it by pyramid. I can't explain because I have to show a few other things. This is Hector SLAM. Never. Hadar show Hector. Okay, let's talk about vision. Vislam. Okay? There are another few families in the vision. Vislam. You will see Orb SLAM. Orb SLAM is a feature-based. There, it's a single camera, and you do SLAM. How we do it? You take in each camera, in each picture, you find features. And the feature, let's say, feature, if you are looking on this wall, this is a good feature. You see, it's quite understandable. Okay, this is also a good feature. Okay, so in each image, you will find features. And then in the next robot moves, and in the next image, you will find another feature. And now it's fine to find the correlation between those features. Oh, this feature I see in the earlier, and I understand how the movement of the camera. And when it understands the movement of the camera, it builds a feature map. Oh, I didn't see you. Sorry. Sorry? No, yeah. Didn't scan everything. Single map, small map. Okay, so this is what you do in Orb SLAM, and you see those features, very unique one, recognize, understand those features, and when he return to the specific place and understand this is the feature that I see earlier, he know how to close also loop here. This is the way you do it, and it moves, find the features, and you see this blue Dots are actually a keyframe. They save key, frame, and they do the correlation between those frames by tracking the feature here and understanding how much, understanding the movement of the camera. This is orb slam. Another is LSD slam. It's called large-scale direct molecular slam. Also, the advantage here is that also understand, compare it to the map, and also do it by images, but it's not understand, not search for specific features, because the problem with searching specific features is using less information of the image. And here, you do it by intensities of the image, and you can get a better corresponding between image, because you have a lot of information. And this is what VSLAM do. And you see here a lot of information and not the small features, and also using also keyframes, and you do the correlation and build the map here. The problematic here is, of course, here and with LSD, if you do it with a single camera, is you don't have the distances. So it's accurate until a scale, specific scale. It doesn't have a scale. There is a problem with when you rotate the camera, okay? There is a problematic, those two algorithms, LSD and orb, fail. If we are talking about a specific location where there is no rich texture, or we can't find features, they have a problem. And one of the latest algorithms are based on convolutional neural network called CNN SLAM. It's they teaching and the specific machine to recognize depths from a single camera, okay, using a neural network. And then you can see this image. You can see this image. This is a depth. The colors represent depths, okay, different depths. And this is the same picture using LSD SLAM. LSD do the correlation between edges, okay, find very good edges, okay. So the problematic here is that it doesn't find edges, but here it finds edges, but here there is also a distance that using the convolutional neural network. And what they do in CNN SLAM, they combine, this is a RGB regular image, the depth that they find is here, and now they also run LSD and find the features and be able to give the distances, because in LSD it's good at the edges. And together, what you can see here is a map using this convolutional neural network, and you build a map and also understand an object in the map, and not only depth but also objects. And
This is for molecular camera.
yeah, for a molecular camera, and the big advantage is to be able to calculate the depth. And another one is also, this is the LSD SLAM. You see they rotating the camera and see what happened to the depths, what happened to them to the map. And this is the CNN SLAM, which is better and accurate. So the main, so you see different algorithm for SLAM, okay? But now what? This is a solved problem. It depends. In the specific areas, it's a solved problem. But now, if you are trying to develop your new robot, and you want it to be at a specific bomb, okay, and you want a SLAM solution that will cost no more than $50, you need to build your own one. There is no off-the-shelf solution. Intel will show us, will show us the off-the-shelf solution, okay, and it start entering a solution for the SLAM problem, okay. But when you actually want to be to work in a mass, you will need to define your own and solve your own problem using, you see, variety of algorithm to SLAM. That's all. Thank you.